In this video, I want to talk about a few results about convergent series. We'll learn a couple of tests, and we'll talk about one type of convergence that's very powerful, and that is absolute convergence. We're kind of thinking of that as something being very super convergent. And the idea is, even if the terms were all positive, there might be some negative terms in your sum kind of oscillating back and forth. So if this is your partial sum, maybe your ANs look like this, so they kind of alternate back and forth, so you get some negative and positive terms that come to some limit. Well, an absolute convergence sequence doesn't really need those negative terms. Everything can be positive and it will still converge. So that's kind of the idea with this absolute convergence. So we say a series is absolutely convergent if the series of absolute values of each term converges. And let me give you a couple of examples. So the first one is -1 to the n over n squared. So we know that the series -1 to the n over n squares, this converges. And this is, you can check this by the alternating series test. It's an alternating series, and you can check that 1 over n squared satisfies the two properties that you need to use the alternating series test. And we know that the absolute value of this, which is just, well, the only thing that could be negative is that -1 to the n. So this is the same thing as 1 over n squared. This converges by p series. So -1 to the n over n squared is an absolutely convergent series. However, -1 to the n over n is not absolutely convergent. So we know that -1 over n converges, or -1 to the n over n converges by the absolute series test, or sorry, the alternating series test. But we know that the series of 1 over n, without the negatives in there, so this is the absolute value of this series, this diverges. And you can say this by many reasons, but p series is probably the easiest to see it. This is a p series where the power is not bigger than 1. It's exactly equal to 1, so we know that this does not converge, it diverges. So this guy here is not absolutely convergent, since these two things here are true. And we call series that aren't absolutely convergent, but still converge with kind of the negative terms in there, we call them conditionally convergent. Now let's look at this result here. So this is a really important result. It basically says that if you know a series is absolutely convergent, well, the underlying series with the negatives in there is also convergent, which is fantastic. Being absolutely convergent is a very powerful thing. And let's show why. So let's assume that the if part is true, that our absolute series is convergent. So let's say the sum is this value L. Well, if this converges to L, then 2 times the series, multiplying every term by 2, just gives us 2L. So we know that. So that means that the series 2 times the absolute value of AN converges. Okay. The other thing to note is that if we look at AN plus the absolute value of AN, that's always between 0 and 2 times the absolute value of an. And in fact, not only is it between these, it's either equal to 0 or equal to 2 absolute value of an, depending on if an is negative or positive. If it's a negative, then these guys cancel and you get 0. And if it's positive, then the absolute value is doing nothing, and you get 2 times the absolute value of an. But for our purposes, that's all we care about. Okay. So the reason that we care about that is that we can use the comparison test. We know that the sum of an plus the absolute value of an is less than the sum of 2 times the absolute value of an, since that's true for all of our terms here. So we know this is convergent. That's what we said above. That had a sum of 2L. So that means that this guy here converges, since it's less than this convergent series. So let's say this series here has a sum of k. And then we can just do a little bit of algebraic manipulation. So we have the sum of an. Well, that's the same thing as the sum of this guy minus the sum of this guy. And if we work that out, we get that the an's cancel here. Since this is just a bunch of things added together, you get commutativity and you can move things around. Everything cancels and you're just left with this an. But this guy had a sum of k, and this guy had a sum of L. So the sum of an is k minus L. Hey, it has a sum, k minus L. These are two numbers. We're just subtracting them. So that tells me that an, the series an, converges, since its sum is some number k minus L. So let's look at an example here. So we have this series, cos of pi over 3n divided by 2 to the n. That's our series, and we want to determine if that converges. Now, before we go on, I want to talk about how I'm thinking about this. When I'm thinking about cosine, I know cosine is bounded between -1 and 1. So I'm thinking that this is going to be like 1 over 2 to the n. It should kind of behave like a constant over 2 to the n. So I'm thinking that's like 1/2 to the n. So I'm thinking this is like a geometric series. However, cos of pi over 3 to the n is kind of hard to get a handle on these exact values here. You probably could, since cosine is periodic, but we don't want to do something like that. But this is where the ideas that we talked about on the last slide come in. Cosine is going to be positive and negative depending on what values of n we have in here. But if we think about this in terms of an absolute value, if we put absolute values here, we don't really care what this is. We just care that it's smaller than 1. So that's what we're going to do. We're going to show that this series is absolutely convergent. So let's look at the absolute value of our term. So cos of pi over 3n over 2 to the n. And 2 to the n is always positive, so I'm not even going to write the absolute value of that here. But I know that cosine of pi over 3n, that's between -1 and 1. So the absolute value is between 0 and 1. So that's great. So that is indeed less than or equal to 1 over 2 to the n, which is 1/2 to the n. So I know that 1/2 to the n, this converges by being a geometric series. If you like, you can rewrite this to get in the same form as 1/2 times 1/2 to the n minus 1. And let's be kind of clear with our indices. So let's say we're starting at n equals 1 to infinity for all of these. So this would be n equals 1 to infinity. But we know this is indeed a geometric series, so it converges as long as our ratio is less than 1 in magnitude, and it is. So we know this converges. So we know that this converges since we have the sum being less than a convergent series by the comparison test. And then, well, we know that the absolute value of this converges. It's absolutely convergent, which tells me without the absolute values, it converges as well. So I know that since it's absolutely convergent, then the series without the absolute values is also convergent. That's what we learned on the last slide. So now we're going to use the idea of absolute convergence to help us out here. We have a new test, and it's called the ratio test. And the ratio test is a very, very useful test. In fact, I would say it's the most useful test that we're going to learn. It comes up all of the time, especially when you have things like exponents or factorials in your series, which happen quite a bit, and we'll see that in the coming classes. So if we have a series an, then we know something about the convergence of the series by looking at the limit of the ratio of two consecutive terms, an plus 1 over an. So if we look at that, if this limit gives us indeed some actual real number L, so L is indeed a real number. In fact, it's a non-negative real number, so I'll just put here non-neg. Since we're taking the absolute value, there's no way for it to be negative. If this number is less than 1, I know that the series converges. Conversely, if it's greater than 1, I know that the series does not converge. It diverges. And the only case that we didn't talk about is when it equals 1. And if it equals 1, we can't say too much. There's no real conclusion. We have to try another test. So let me kind of do a sketch of why the ratio test is true. I'm not going to prove it in detail, but we can talk about what's going on. So the idea here is as follows. So if we're thinking about this, we're dividing one term by another. If this was a geometric series, we would get a fixed ratio r, and then the idea of r being less than 1 applies. So if the limit is less than 1, so let me kind of draw a number line here. Here's 1. Here's our limit. And I'm going to take the average of 1 and the limit. This is going to be 1 plus L over 2. Well, this could be a ratio R. And I can use the comparison test to compare this series here, or an, with some term whenever it starts getting eventually small enough. There's some fiddly details I don't want to get into, but at some point the ratio between the terms is smaller than 1 plus L over 2, since the limit is L. It must be at some point you pass that threshold of 1 plus L over 2. So I can compare an with this guy here. I know this guy converges since this is indeed a geometric series with ratio 1 plus L over 2, which is less than 1. So I know by the comparison test, the sum of an must converge, and it converges absolutely too. So that's very important. In the divergence case, so I'll do that in this red pen, I guess. So rather than being eventually smaller than 1 plus L over 2, it's going to be eventually bigger than 1 plus L over 2. And I'll draw the diagram. Maybe I'll draw it in green this time. I know I should have drawn it in red, but it's too late. So in this case, we have our L being bigger than 1. So the average of L and 1, the point in between, 1 plus L over 2, this is greater than 1. We're thinking of this as a ratio. So a geometric series with ratio 1 plus L over 2, where L is greater than 1, we know is going to diverge. So it's going to be the same idea. This guy has to be eventually bigger than 1 plus L over 2 since it's approaching L. So if we take the ratios eventually have to be bigger than 1 plus L over 2, which tells me that this sum, AN, is eventually going to be bigger than this guy here. And by the comparison test, rather than converging, it diverges, since that geometric series is a divergent geometric series. Since this ratio is bigger than 1, this guy we know is going to be bigger, so it diverges. In the last case, I just need to show you that both behaviors can hold. So we're not going to worry about the absolute values because all of the terms in both series are positive anyway. So we'll just take the ratio. So if we take the ratio of AN plus 1 over AN, like we're doing here, and we take the limit, I can leave this as a little small exercise for you guys, but it should be fairly straightforward to realize that you're going to have the same degree leading term in the top and bottom. They both have coefficient 1, so the limit is going to be 1 here. And we know by P series, this guy converges. So this converges by P series. Great. Now let's look at the other series that I want to talk about, 1 over n. This is the harmonic series. I know this diverges. And there's lots of ways of showing it, but by P series is probably the easiest way. We can just say it's a P series where P is 1. 1 is not greater than 1. So this guy diverges. All right. But if we take the limit of 1 over n plus 1 over 1 over n, so that's an plus 1 over an. Again, I'll leave the details as a little bit of an exercise for you guys. But you can see that the limit is also 1. So we have two different situations where the limit is 1. We have the limit as being 1 for a convergent series, and we have the limit being 1 for a divergent series. So both behaviors can happen. So when you have a limit of 1, that doesn't tell you anything. You need to do a different test. So let's do an example here. So let's have this series. This looks fairly complicated. We have negative 1 to the n. We have a 2 to the n. We have times some sort of polynomial n plus 1, and then our denominator is n factorial. So kind of our other tests might be kind of hard to use. We could think about the alternating series test, but that, again, might be hard to show. But the ratio test is a perfect choice for a test for this type of thing. And the reason is, and we'll see, when we have a bunch of things multiplied together, like 2 to the n is just n2's multiplied together, and n factorial is all the numbers from 1 to n multiplied together. When we divide the n plus 1th term by the nth term, we'll have a lot of cancellation. So that's how you can tell when to use the ratio test. So let's have a look. Let's look at the limit as n approaches infinity of the absolute value of an plus 1 over an. And I will say, usually it's easier to see what's going on if we write it like this. The absolute value of an plus 1 divided by 1 over the absolute value of an. And that's especially useful when you have kind of a fraction here, because you can easily see what cancels. So let's go ahead and do that. Let's plug in n plus 1 to all of our terms. Notice that this negative 1 to the n, if we're taking the absolute value, that's just going away. We don't care about the sign of it, so I don't even need to write that down. So this is going to be the limit as n approaches infinity of 2 to the n plus 1 times n plus 1, which is n plus 2, over n plus 1 factorial, and then divided by 1 over an, which is 1 over this guy. So I'm just going to flip the numerator and denominator here. So I'm going to make it times n factorial over 2 to the n. Remember, we're dropping that negative 1 to the n since we're taking the absolute value, times n plus 1. And we'll put our absolute values back, although we don't really need to because everything is basically positive in here anyway. Okay, so here's where we get to cancel a lot of things. We see we have n plus 1 2's here and n 2's here. So all of these n 2's cancel off with all but one of those 2's. For the n plus 1 factorial, well, that's all the numbers from 1 up to n plus 1 multiplied together. This is all the numbers from 1 to n multiplied together. So we can get rid of all of these guys, and we're only left with an n plus 1 in the denominator here. Let me kind of write that out to the side. So this is like 1 times 2 times 3 all the way to times n. So that's n factorial over 1 times 2 times 3 all the way to times n plus 1. That's n plus 1 factorial. So everything cancels here except for that n plus 1 in the denominator. And we can't really simplify the n plus 2 and the n plus 1, but we know how to take limits of ratios of polynomials, so that's not going to be a problem. So let's simplify this, and what do we have? The limit as n approaches infinity. I'm going to not write the absolute value since everything's positive. So we have 2 times n plus 2 over n plus 1, so that's from the n plus 1 factorial, times n plus 1, but that's another n plus 1, so I'll just say it's n plus 1 squared. And now we can use our ideas of limits, and we just have a polynomial left. Up top, we have a term, the leading term has degree 1, it's just n. The bottom, the leading term, is going to have degree 2, it's going to be n squared if we multiplied this out. So I know that since the degree of the bottom is bigger than the degree of the top, the limit here is going to be 0. And 0 is indeed less than 1. So that tells us that our series converges. Okay, let's do this one. This one looks a little different. So we have this negative 1 to the n. And when we see that, we're thinking that might not matter. But this term is a little bit complicated. So the bottom's not too bad. We have an n factorial. But the top, we have just the even numbers up to 2n multiplied together. So still n numbers, but the even numbers up to 2n. So let's determine the convergence of this, and let's do it two different ways just for practice. So let's do it using the ratio test. First, And then let's show another way of showing the convergence of it, or the divergence of it, using geometric series. So let's do the first one first. Let's take the limit of the absolute value of these guys. So again, I'm going to write this as the n plus 1th term times the reciprocal of the nth term. So I'm going to get 2 times 4 times 6 times all the way to 2n times 2n plus 2, since we're just writing down the first n plus 1 even numbers, and that's divided by n plus 1 factorial. And we're going to multiply by the reciprocal of our term, n factorial over 2 times 4 times 6 times all the way to 2n. And again, the ratio test was a good choice because we had a bunch of things multiplied together here. So hopefully you'll have a lot of cancellation that'll simplify things. And in this case, we have loads of cancellation. The numbers 1 to n cancel with the numbers 1 to n here, so we're just left with an n plus 1, just like in the last slide. And here, all the numbers 2, 4, 6, all the way up to 2n cancel with all of these guys. So we're just left with the limit as n approaches infinity of 2n plus 2, which I'll write as 2n plus 1, 2 times n plus 1, over n plus 1. Obviously, these guys cancel. So this is the same thing as the limit as n approaches infinity of 2. Well, there's not even an n in there anymore. So the limit is, of course, 2. 2 is greater than 1. So our series diverges. Great. So it will grow without bound. And we could check this if we want using partial sums to see that indeed it does grow without bound. Even though it alternates, these terms are getting bigger and bigger and bigger. So it's going to kind of alternate between getting positively bigger and negatively bigger, and it'll oscillate a little bit and grow at the same time. So that was part 1. Part 2, I'll do this in blue, just to keep things straight. I'll do it up here. We want to use the idea of geometric series. And the whole idea with this one is that n factorial and this product of n even numbers is almost the same, except each of these numbers has an additional factor of 2 in it. Rather than 1, 2, 3, 4, 5, 6, all the way up to n, we have 1 times 2, 2 times 2, 3 times 2, all the way up to n times 2. So we can factor out all n 2's here. So this is going to be, we have this negative 1 to the n. We're going to factor out these n 2's. Remember, there is a 1, 2 here, another 2 here, another 2 here, all the way up to our nth 2 here. And then we're left with 1 times 2 times 3, all the way up to times n. And that is n factorial. And that's over n factorial. So they'll cancel, and we're left with the sum of negative 1 to the n times 2 to the n, so we can combine those and make it negative 2 to the n. And we know the ratio here is negative 2, so we're not even worried about getting it in the correct form. We can just immediately say that since negative 2 isn't in the interval from negative 1 to 1, that's our convergence interval for geometric series, we know that our series diverges, by geometric series. another similar test is the root test. I'm not going to go into kind of the proof of how this is true. It's just slightly more complicated than the ratio test, but the idea is basically the same. But we can just talk about the result. And it's, if you have a series and you take the limit of the absolute value of a term to the nth root, which I wrote as to the 1 over nth power. In books, you might see instead the limit as n approaches infinity of the absolute value of the nth root of an. You might see that instead. Or sorry, I have it the wrong way around. The absolute value goes inside, so it's the nth root of the absolute value of an. If that gives you some number L, the same type of convergence properties hold compared to the ratio test. If your L is small, then it converges absolutely. If your L is large, so large bigger than 1, you know that your series diverges absolutely. In fact, we don't even need this word absolutely. Let's just cross that out. It just diverges. There's no such thing as diverging absolutely. And if L equals 1, then there's no information. And a good time to use the root test is when you have a term to the nth power or something like that. So let's go ahead and do this. So using the root test, we're going to take the limit as n approaches infinity of the absolute value of our term, 2n plus 3 over 3n plus 2 to the n, that's our term, and we're going to take the nth root of it, or the 1 over nth power. And you can see exactly what's going to happen. The nth root and the nth power are going to cancel, and this is going to be the same thing as the limit as n approaches infinity of 2n plus 3 over 3n plus 2. Again, using our limit rules from 1105, we can see that we get 2/3. We have the same degree of the leading term for each part of the numerator and denominator. So we just take the ratio of the coefficients, 2/3. And we know 2/3 is indeed less than 1, so our series converges. And that's how the root test works. Now that we have a lot of tests, we have the integral test, we have the alternating series test, we have the ratio test, we have the root test, and we have the comparison and limit comparison tests, it's good to go over approaches for when to use each of them. And again, this is just a heuristic. This isn't kind of a plan that always works. But let's just go over some good ideas about which test to choose. So, first, a really good idea is you should always eyeball your terms. See if you can do the limit in your head and look and see if the limit is going to be something other than 0. If that's the case, if the limit comes to some value that isn't 0, you know the sequence diverges by the test for divergence, and you don't need to go any farther. So that's what I always do when I look at a series, is just see if the test for divergence is going to be applicable. Okay, so let's say you do that, and the limit of the terms is indeed 0, so you should check if it indeed does converge. Well, the first thing is ask yourself, is this something I know that converges or diverges because it's a known type, like a geometric series or a p-series, or maybe it's a telescoping series, and if you know that, well, you can just use your knowledge to be able to almost immediately say the convergence of the series. Well, maybe it's not exactly a series, maybe it's close to a series. If it's close to a series, and you can kind of use the comparison or limit comparison test, that's a really good idea too. And you could think, well, maybe some of the terms will be negative, so what can I do there? Consider testing for absolute convergence. In fact, that's always a good idea. If you can show absolute convergence, you know that the series itself converges. And we did an example like that earlier in the video. So check if it's close to a known type of series. Then, well, maybe it's an alternating series. Well, if it's an alternating series, see if you can do the alternating series test easily. If so, you're good to go. The next thing, well, does it have lots of things that could cancel, like factorials or powers? If so, try the ratio test. Lots of cancellation will happen, and it might be an easy thing to do. However, you might get nice cancellation, and it turns out that you get a limit of 1. And in that case, you're going to have to go back to the drawing board and try a different test. So here, if you get the limit equals to 1, try a different test. And if it's of the form some term to the power of n, consider the root test. That's probably a good way to go too. If you look at the term and you're like, I could probably integrate that if that was a function, you should consider the integral test. Remember, with the integral test, it's a little more complicated than the other ones. There are some hypotheses you need to check. You need to make sure that your function is eventually always positive, that it's eventually always continuous, and that it's eventually always decreasing. So you need to check that. And maybe you can't see what's going on right away. If that's the case, then just try some things. Calculate some partial sums, see if you can just determine if it's likely to converge or diverge. Or just try some comparisons. So it's always a good idea to try some, and it can be limit comparisons. You might be able to get lucky. And if you think it's going to converge, try comparing it with 1 over n squared. And if it's going to diverge, try 1 over n. You just might luck into the correct thing to compare it with. A few other hints that come up. Remember that if you see a trig function, like especially sine and cos, they're always bounded between -1 and 1. I don't know why that's a negative there. That should be a positive 1. You can think of these guys behaving like a constant. The second kind of hint I want to give you is think growth rates. Constants don't grow. Logarithmic functions grow faster than constants. Polynomials grow faster than logarithmic functions. Exponentials grow faster than polynomials. Factorials grow faster than exponentials. And exponentials, where the power is squared, grow faster than factorials. So that might kind of help to determine whether something is going to converge or diverge. And the third hint is think about stringing some tests together. That might be something that has to happen. So consider maybe proving convergence of a simpler series, and then using some sort of comparison to the series that you're starting with.